So today we're going to talk about the idea about abstractions via mathematical models. And this is extremely relevant to your lab number 5, the last lab, and also the lab test number 3, which will be based on this lab as well, as I broadcast an email to you yesterday. Okay? Let's now try to talk about ideas about abstractions, mathematical models. First of all, I would like to review very quickly about what we learned from before the lecture. Actually, this is a lecture we did before lab test 1, okay? You can always refer back to the lecture about complete contracts. So we want to just, today the main goal is to do things in a better way. So what we did before about complete contract using deep twin and also across, it's already a very reasonable approach. We want to do even better, okay? Let's just review very quickly one single slide, just a few more points. So if you still have doubts about what deep twin or across, how you can make things combine together, you can refer to the complete contracts lecture. Okay, that's what you can do. Okay, let's just review this point very quickly. So in the post condition specifically, we know that for each attributes, we have to specify the relationship between the pre-state and post-states. Again, the pre-state means the state of your objects before the command or query is executed, and the post-state is the state after the command is executed, pre-state and post-state. And usually the way we do it is by using an O keyword. Okay, that's what we learned from before. Now, what's really tricky is about the composite structure attributes, especially let's say your attributes of type array or linked list. In which case, you got to make sure two things. Okay, let's review the points. First of all, let's say I'm trying to add an entry into the dictionary. In that case, I want to make sure the new entry has been created into the dictionary. Not only that, but also the rest of the dictionary is untouched. So that's the tricky part. So we want to make sure the new bit is there, and also the rest of the original structure is remain untouched. Okay, so these are the two main points you got to make sure. So this is something we covered previously in the complete contracts lecture. So now, I want to illustrate the point or motivation for this additional lecture on how we can do contracts. So why do we need to do more? And why do you need to do things like lab number 5 and also your lab test number 3, okay? Now, let's apply this kind of technique using across, using deep twin in a last in, first out stack. Just simple enough to illustrate the point, okay? Now, for a stack, we're going to consider 3 different implementation strategies. Okay, again, let me remind you remember the principle of information hiding. Information hiding means if there's anything that's specific to your implementation strategy, you should hide it. And the way we hide it is by exporting attributes to none. Okay, that's what we do. However, you will realize that we can actually refer to the private attributes in the post condition, but you cannot refer to them in the precondition. That's something we found from the previous lab and lab tests. Okay, let's review the strategy very quickly and then I will illustrate to you the points. So let's say we got either an array. In the case of the array, the last element in the array is the top of the stack. And then we also got another 2 strategy for linked list. Let's say for strategy number 2, we treat the first element in the list to be the top. In the strategy number 3, we treat the last element in the list to be the top. You can see that depending on which strategy I'm talking about, I may have to do the post condition that's really related to that particular strategy. So that's something we'll see that's quite a shortcoming. It's going to violate certain principles. We'll see. First of all, let me show you what it can do according to what you learned. Okay, for these 3 implementations, if you want to say what's the count for the stack, what's the size of the stack, you can simply say imp.count. Let's say the imp can be of different types. Imp can be of type array, or it can be of types linked list. You should be very familiar with both already. Now, what about the top? So this is the thing. Depending on which strategy we are talking about, the top might be different. For the case of the array, the last element in the array will be the top. Okay, imp at position imp.count. Also, for strategy number 2, we're gonna treat the first element, the head of the list, to be the top. In that case, we'll say imp.first. So these are all the features from the relevant classes. Okay. And number 3, we got imp.last, which means in this case, we are treating the last elements in the list to be the top. Okay? Guys, following so far? Okay? Basically, we just get different strategies. You can choose whatever you like. And then, what about push? If we want to push onto the stack, For strategy number 1, we're gonna add it to the last, right? In that case, we can use a force. In strategy number 2, what should we do? Should we add to the first or add to the last? Add to the first, right? Because we are treating the first as the top, okay? What about strategy number 3 in this case? Add to the last, right? Because we are treating the last as the top, right? You can see that depending on which strategy you're choosing, even though for strategy number 2 and 3, you're using linked list, but you may want to do things differently, depending on what's your interpretation for the top. Okay, finally, let's say for the pop. In this case, if I want to remove the top from the array, in this case, I want to remove the last elements, in which case I can call, just imp, so there's a typo, just imp.remove tail, and then 1. Okay? I want to remove the last 1 elements. And then for strategy number 2, I want to remove the first. So what I can do is, I can move the cursor to the front elements and then remove. And for strategy number 3, I can say finish, go to the last position of the cursor of the list, and then remove. Okay? Okay, this table here simply summarizes at least three different ways you can do things. It's quite true in general, because for any particular ADT, like a stack you want to implement, you got more than one way, or you got multiple ways of doing things. Okay? Now, here's a question for you. Given that all the 3 strategies are trying to implement the same ADT, a level stack, do you think the contracts, especially the post condition, are going to look the same? They should, because contracts are supposed to be used to communicate with your clients. Contract, again, post condition are the benefits for the clients, so they should know. But now, do you think depending on which strategy we are talking about, do you think the post condition will look the same? When I say identical, I mean syntactically, or are we going to type out the same thing in the post condition? Yes, I heard yes. Okay. Anyone would say no if you didn't see the slides. Yes, you would say no. Just give me an idea. Why? They got different syntax. Okay, that's one way. Do some. Anything else to add on top?
We're dealing with 2 different ends of a linked list. It has to accommodate for that.
Yeah, exactly. Okay, so basically just rephrase what Dusan just said. Now, the post condition, for example, let's say strategy number 2 and 3. In the post condition for the push, what's going to be the new top? The new top is going to be G that we just added in. Now, how do I express the post condition for strategy number 2 to say the new top is now G? Well, I would say imp.first is G. What about strategy number 3? Imp.last is equal to G. So they're different, even though they mean the same thing. Okay? That's kind of the thing I want to express. Okay, let's see exactly how the code looks like. You will see even more difference. So now let's present the 3 versions one by one. Again, the source code is available for you. You might find them quite relevant to your lab number 5. Feel free to reuse the code if you want to. Okay, now let's say we define something called level stack. There's already a library class called stack in IFO. I'm just creating a different one. Okay, level stack, and then the implementation is now an array. So now for the array, the last element is going to be the top. Okay. Now, first of all, we can create empty array, and then the count should be 0. I'm just using the implementation attribute over here, the private one. Okay, you can see it's exported to none. But we can use it in the post condition. Nothing wrong with that. But I will just illustrate to you, it's not an ideal design. And then for the push, we can do force to the last elements. And then over here, let's try to do this. As I said before, let's specify both the change part and the unchanged part, right? That's actually the rule for composite structure attributes. The change part would be the new top should be the G, right, that we just added in. So we'll say imp at position count is equal to G. Nothing special here. And now what about we want to say the rest of the array is unchanged? You can use a cross syntax, right? In this case, you can say across from 1 to count minus 1. Because at count over here, that's a new top. So from 1 into count minus 1, that should be O1. So we are saying that for these positions, the old model, the old imp and the new imp, they are the same. Guys, any question about this? In some way, I'm just reviewing what we learned from the complete contract. If you got any question, please raise the issue. because I might ask you a question in the lab test. Okay. Good. Okay. Let's go on. Now, what about pop? Similar. For the pop, since excuse me, since we are treating the last element in the array to be the top, if you want to pop, you simply remove the tail, remove the last one elements, and then you do something similar. What's changed? The count has been changed. You can say count is equal to O count minus 1, and also you can say unchanged. In this case, I'm going to say the rest of the stack simply doesn't change. In that case, that's what I can do. I can say again from 1 up to count minus 1, and then the old imp is equal to the new imp. And here I'm using a deep twin. Okay, so that's the first version of the LIFO stack, in which case I'm using strategy number 1, array. Okay, now so somehow I did some visual annotation over here. The things you see on red, you're going to see that the thing on red, for example, you can see the push feature over there. The first in the ensure, you can see for the changed imp at position count is in red. That means if we want to change the implementation from, let's say, from array into linked list, in that case, that might be the part we're going to change. Okay, let's see that. Okay. Now, let's say strategy number 2. Number 2, we are trying to use a linked list, and the first element will be the top. Okay, so kind of the opposite as the array. Now, let's see this. Again, you can say rather than imp.makeEmpty, we'll say make. Okay, that's a small issue. And then imp.count is equal to 0. Now, let's say push over here. You can see the way we do push is also different. Imp.push put front G. Now, any idea? What about the change over here? We want to say now the new top is equal to G. So now we cannot say imp any. Somehow we want to use something that's efficient for the linked list. In this case, we can simply go to the first elements. Right? We can say, so first over here, it's a linked list specific feature. It is not available on the array. So that's why you can say imp.first is equal to G. Okay, one more thing to show you. You can see imp.first is equal to G, as opposed to the previous one. You'll see that imp at position count is equal to G. So they're different. Even though they're trying to specify the same thing abstractly, it's trying to say the top of the stack has become G. But because of the implementation strategy that's different, you're going to say it differently, okay? Which is not very convenient. Why can you not say the same thing in the same way? Why do you have to change the way you say things just because the strategy is different? Okay, that's kind of the insight, which I'll summarize in just a moment. Okay, let's say that's so strategy number 2. Now, how do we say unchanged over here? In the case of the array, we say that since the last element is the top, so that's why from 1 until count minus 1 is unchanged. But now for the linked list, because now the first is the top. So now that means from 2 until count should be different, right? Again, abstractly speaking, the idea is really the same. You want to say the top has been changed and the rest of the structure is unchanged. But now because the way you treat the top is different, you can say it differently. For example, you can see that. I'm going to say from 2 until count. Right? Let me just illustrate something very quickly for you, just in case you're lost. Okay, we have strategy number 1. Okay, over here we have an array. Okay, let's say we have some stack over here. Let's say S of type stack. S dot push Alan, and then S dot push Mark, and then S dot push Tom. Okay. Now for strategy number 1, sorry, I want to erase that. Okay, this is the stack operation we are trying to reason. So now let's say strategy number 1. Strategy number 1 over here. So now we know that the last element is going to be the top. Okay. In this case, we know that eventually what we will get is Tom and Mark and then Alan. That's how it looks like. Abstractly speaking, this is the stack we are talking about. This is stack. Alan, Mark, and then Tom. This is abstractly speaking. And this is strategy number 1. What about strategy number 2, very quickly? For strategy number 2 over here, you will have a linked list, in which case you got a chain of 3 different nodes over here. But now remember, for strategy number 2, we are treating the first element here to be the top, okay? So that means this is the top. So what we will get is kind of in the reverse order. So what you will get is Tom, Mark, and Alan. Okay, you can see that over here, right? So in this case, the order in which we are trying to organize the things internally is completely hidden from the user. It should be hidden. But somehow you can see back in the contracts over there, we are actually exposing these kind of details to the users. Okay, you can see what the issue is, right? Okay, now one more thing. You can see that over here. Now, in the case of strategy number 1, how do we express the rest of the stack? We're going to say from count equal to 1 until count minus 1. And then in the case of strategy number 2, how do we express the rest of the stack? From position 2 until count. Okay, again, the same idea abstractly, but in terms of the concrete implementation, you're going to express that differently. Okay, that's really the issue. Okay, so you can see also pop over here. Okay, guys, any questions? If you got any confusion, it's now time to complain. Otherwise, we'll get to the new design. Yes? Of course. Yes. Yes.
So strategy 2, where you have Tom, Mark, and Alan.
Mm-hmm.
If you want to do Alan, Mark, and Tom, just like the array, just like the...
Oh, okay, it's different. Okay, let me just emphasize that. Okay, first of all, abstractly speaking, we are dealing with a stack over here. A stack, conceptually you can think of a stack is just like that. So Tom is the top. However, the way we implement this stack is different. Okay, in strategy number 1, the last element in the array is always the top. That's why it's organized in this way over here. And in strategy number 2, again, Tom should still be the top and Alice should still be the bottom. In this case, of course, it's going to be organized in this way, where Tom is the first element. Okay, yeah, that's why. Okay. So now again, it's very important to really understand, abstractly speaking over here, the stack is always the same, Tom, Mark, and Alan. Depending on which strategy you have chosen, you may have to write your contract differently accordingly. Okay, that's really the issue here. Okay, and I'm going to show you why this can be problematic. Okay, now very quickly, now strategy number 3, yet another strategy. Now this strategy over here is a linked list, but now rather than treating the first element to be the top, we are treating the last element to be the top. Okay, now you can go over the code yourself, and now we're going to say aim.make over here, and then now what about the push? We're going to extend to the end, right? And then we're going to have changed, in this case, the new top should be G. In this case, rather than imp.first in the previous case, right? In the previous case, we say imp.first. Now we say imp.last, right? Because we are talking about different strategy. Okay, and then unchanged. Now we want to say, how do we specify the rest of the stack in this particular strategy? From count 1 until, from 1 until count minus 1, right? That's how we do it. And then similarly for the pop, we do something similar. I'll leave that to you. Okay. So guys, that's the 3 versions of the stack according to how we learned before. Nothing wrong so far. There's no mistake. I'm just trying to say, in terms of design, this is not the best design you may have. Yes?
The count changes once you pop, and post condition it ensures up to the count minus 1.
Uh-huh.
It should be old count minus 1, or it should be just count.
That's a good question there. You're right, because now if you say count is equal to old count, so that means the count is already decremented, in which case you will do, you know what, I'll look into this. I think you're right. Okay, maybe there's a typo I gotta fix. Okay, it's a logical error actually. Okay, so guys, the question was, over here, how do we specify the count is unchanged over here? So now in the case of the pop over here, count has been decremented. So now the upper bound over here, should it be count minus 1 or count? I think it should be count. You're right. Okay, I'll fix that. Good. Very good. Very good. I'm happy to hear that. Okay, now let's review what we have achieved so far, and let's see what's the flaws of the design. Okay, so the post conditions are complete for all the three versions, pretty much consistent with how we did complete contracts in the previous lecture. Now, so we say that the new top and also the remaining of the stack, okay? Now, the thing is, they violate the principle of information hiding, okay? Again, before we can justify that it violates this principle, we gotta review what the principle really is, right? What's information hiding? Anyone? Give a try. Information hiding. Say it again. Hiding the implementation from the user, exactly, very good. Which means whatever you do for making a strategy for implementation, they should not be revealed to the user. Very good, okay? Very important. Okay, I'm just phrasing a slightly different way, but it's the same, okay? Now, how is that the case? Based on what we have seen, can you see how the information hiding principle was violated? Just give me one example. How? Yes, please. It's different? Yeah, exactly. Now, let's just see that very quickly. For example, in version number 3, you can see that in this case, we say imp the last because we are treating the last element of the list to be the top. On the other hand, in version number 2, over here, since we are treating the first item to be the top, that's why we say imp the first. So they're different, okay? So now when your customer or your client see this contract here, they kind of know, oh, so now in this case, you're treating the internal list, the first item to be the top. But do they really have to know this information? They don't. They just want to know that the top is somewhere, right? It has been, the FIFO property has been maintained. They don't have to know whether the front or the end is the top. They don't need to know. It's irrelevant to them, okay? So you're exposing the implementation secret to your client, which is not good. Okay, so now exactly, so you can see in version number 1, this is how you express the top. In version number 2, that's how you do it. In version number 3, okay? So now you shouldn't do that. And also, how do you specify the remaining part of the stack? In version number 1, it's from 1 until count minus 1. Actually, I may have to change that anyway, okay? And then for version number 2, should be from 2 to count, okay? Now, in this case, let's go one step even further. Let's say this. Let me ask you this. Let's say I'm currently in version 1. Let's just imagine this hypothetically. Let me just show you this. Let's say this is version 1 I have, version 1. Now, version 1 uses an array and then treat the last element to be the top. Let's say I want to migrate my code. I want to change that as an implementer. I want to migrate to version number 2, in which case I'm going to change from array into linked list. And also I'm going to treat the first item to be the top. Now, question for you. Are there going to be multiple places of the contract I need to modify? Or a single place? Multiple or single? Multiple, right? Just tell me which one, for example, I'm going to change. Anyone? Yeah, want to try? One place. Hey, where should we change? Yes, exactly. That's one place. Can you give me another place? Maybe another feature, for example. Any other place? Well, you can see that if I change to version number 2, where the first item is the top, in that case, the way I specify the remaining part of the stack going to change as well, right? It's going to be from 2 until count. That means for the pop feature over there, I also need to change the second post condition, right? Rather than saying from 1 to count minus 1, I should say 2 to count. Right? Again, that's going to be another place to change. Okay? That's something you should really run in your head to make sure you're convinced. Okay, you can see to version 2, for example, this is the first place to change. First place, second place, and also third place. So multiple places. Now, what do we have? That means if you want to make a change to your software, there are actually multiple places you have to change. So what principle does this violate? Single choice principle, exactly. Okay, single choice principle. There should be only a single place they should change. Okay, so now in this slide over here, we try to argue that what we learned before for the complete contract, the solution there is sound. It does not cause any logical error over there. However, as far as the design is concerned, it's not a perfect design. It violates the single choice principle, also violates the information hiding principle. Okay, you want to see why. Okay, now, question is, how do we change this then? Okay, basically, the way to change this is we want to have a unified way of writing your contracts in your precondition and postcondition. And whenever you change the implementation from one into another, you should not need to modify the pre or postcondition. But how do we do that? Okay, and the way to do that, let me show you the code first, the first version, and then let's see how things can be done. Okay. Okay, that's really, now you start, up to now, it's still something that's not really new to you. So now let's do something new, okay? So over here, let's say we got lethal stack. Also here, when we have dash greater than, it's the constraint genericity that we talked about last time. Okay, it simply means now, let's just extend this a little bit. This one is just implementation specific. You don't have to worry too much. Just to say, we're going to use a particular library called a mathematical library, in which case every element must be not void for void safety. That's why we say G must extend attach any, which means it's always attached. For this line here, you don't have to worry too much. Okay? So now let's go back there. Let's say for strategy number 1. Okay? Now this is a new bits. Okay? Let's try to see what this really means. First of all, we declare another query here called model. And the model is of type sequence of G. Okay? So now let me show you something. When you actually open up your sample code or your projects, you will see that under libraries over there, there's something called math models. Okay? So this is what we are teaching you over here. We're trying to use a library there for you to write contract that will obey information hiding and also single choice principle. How do we do that? Under mathematical models there, let me show you very quickly. Under collections, there are several, quite a bunch of classes you need. I'm going to talk about sequence and also relation today. For the lab, you are going to need the function called, class called func, which is function. Okay, that's what you need for the lab. And for the lab test, I'll tell you which one you need, but you better kind of get a feel about how you can use every one of them. But for the exam, you're supposed to know both the relation and the set. Okay, it's actually set in the slides at the end. Okay, let me just let's see how we can do that. Okay, let me give you some idea over here. Okay, let's just go back to iPad. Let's see how conceptually how this works. Okay, you also have some diagram in the slides, but I'll just draw from scratch so you can see that. Okay, so now let's say this over here. So now let's say I have my implementation over here called array of type array. Okay, this is my implementation. Okay, now let's say I'm trying to do push. Let's consider just push feature. Okay, push some elements of G. Let's say I'm trying to do that. So let's say this is the old implementation. And then somehow after the push operation, what I will do is I'll try to do imp dot force and then pass some argument over here. You can see from the previous slides. And what I will get is just another imp over here. Okay, so far so good. Okay, now the issue from the previous design was like as follows. Let me use different color. Because rather than array, I can also try to do a linked list. Linked list over here and also of type G. And also, after that, I can also get a new imp over here. But how do I go from the old imp to the new imp? The way I do it is by imp dot put front, for example, and then G. Okay, that's the second version. Okay, let me just put the third version just for completeness. And also, the third version there, you can also change the imp from linked list. Also linked list, but now we are treating the last element to be the top. So now what you will do is you will say imp dot extend. Extend G over here, and then after that you just get another imp. So you got 3 different versions. Okay, as we learned before, if you simply expose these implementation details into the contracts, you got to get different contract for the same feature from version to version. Now the idea is as follows. We want to completely hide these. We want to hide these completely. Okay, let me just use this over here. Okay, let me draw a border over here. That means anything that's below this line here is completely hidden. But now, what should we show to the clients? We want to show something to them that's irrelevant, that's completely independent from the implementation details. Math models. Math model, briefly speaking, I'll give you more details. So over here, what we will do is, I'll give you one example over here. Let me use green. So now over here, I'm going to say model over here, model of type sequence. So the sequence over here is simply a immutable mathematical sequence. When I say immutable, I'll show you in just a moment, which means you can easily just to get a current sequence and see what's going to be a variance version of that and compare them. Okay, I'll show you in just a moment. Okay, so now over here we want to say that abstractly speaking, for the push operation there, I also have over here, let's say that's the old model, and this is the new model after the push. New model after the push. Okay? And then I want to say the way I link these two is as follows. Okay? Now let me just give you one example right away. So let's say if currently I have my stack that looks like this. So let's say that it be consistent with the previous one. So we should get Tom, Mark, and Alan. Okay? Let's say. Let's see what the sequence is. So we got Alan, Mark, and Tom. Okay, this is a sequence. Okay? This is a sequence for the clients to read. So now that means we always treat the last elements in the sequence to be the top. Always the case. So irrelevant to what kind of implementation you have. Irrelevant. Always the last one. Okay? Now, when I go from the old model to the new model here, what can I write? What I can write is something like this. I can say the model. Okay, let's see what the new model is, first of all. Let's say I want to say push Jim. Okay, so what do I expect to see to be the new model? In this case, it would be something like this. It would be Alan, Mark, Tom, and then with Jim. Okay, in this case. Now, this is the new model. This is a new sequence. So this is a new model. Now, in terms of the contracts, how can I compare these two models, the old model and the new model? What I can say is, I can say the new model over here. Okay, let me just highlight the thing you should really pay attention to. Over here, you can see this is new element that's added. Okay, I can say the model over here is, tell that is equal to the old model. Okay, you're going to say the deep twin, I'll say dt over here, and then dot appended with G. Okay, like that. Okay, so now this feature over here, appended. Okay, let me show you very quickly. This one is not a command, it's a query. Okay, if you go to the iPhone Studio, I'll show you how you can look for that. Okay, so now if you go to sequence over here, okay, sequence over here, and then you can type appended. Okay, so you will see that appended is over here. Okay, appended is actually a query which returns something. So when I say like current, which means it's going to be a type that's the same as the current class. In this case, because I'm in sequence, so it's going to return to me a sequence. Okay, so now what I'm trying to say, so first of all, I just want to show you that it's really a query, not rather than command. Okay, let's go back here. So what I'm trying to say over here is, so now over here I can say, let me just try to highlight different things. So old model over here, and then the model. And what's the difference between them? The old model over here is simply whatever the old model is, appended with Jim at the end. Okay, that's the contrast. And now we want to make sure this contrast stays the same always. But now the question is, what if the implementation changes? If the implementation changes, we're just going to change the way we define the model. Okay? Let me just draw some arrows and I will draw another new things to show you. Okay, now, how do we draw connections between the implementation and the model? We're going to define something called abstraction function. Okay, what's really abstraction function? Basically, the principle is very easy. Take some implementation, you want to return the model, in this case, sequence. How do we do that? So now, let's say for strategy number 1 over here. For strategy number 1, I will simply convert from the array into the model over here. For strategy number 2, which is in blue, I will try to convert from linked list into the model over here. And then for strategy number 3, I will simply convert from also linked list into the model. Okay? Conceptually, that's the case. Okay? I'll leave the diagram like this, and I'll go over some code with you to make some concrete sense, and then I'll redraw the diagram in a different way to help you understand. So this is the most critical bit for today. Once you get an idea, you're ready to do lab number 5. Okay? Let's see this very quickly. Let's see the code. Okay? Now, you will see that I'm going to show you the 3 versions of the implementation for leaflet stack again. What you will see is as follows. That's something I want you to keep in mind first. You're going to see that the way, whenever we change from one version to another, the only thing we'll change would not be this contrast anymore. This contrast stays the same always. However, the only thing we change is how we go from the particular implementation to the model. That's the only thing. Okay? We'll see. Let's see how this happens in programming. So now in this particular case here, okay, one more thing to remind you. And we also have some assumption over here. We say that over here, let me just write it out also explicitly over here. So here we have the model, the sequence over here, the sequence here. So now we have some assumption here. The last elements of sequence is the top. That one is going to remain invariance. That one doesn't change. Okay? Let's see how we can do different implementation conversion. Okay, now, this case here is very easy. In this case, we are trying to convert the array into this particular sequence. Now, remember in the strategy number 1, we are also treating the last element in the array to be the top. In this case, it will be as easy as just to say, we also got some feature in the sequence class called make from array. You can look into that. It's basically just follow exactly the same order of the array and insert it into the sequence. This case, there's no tricky points. But if we go to version number 2, because we are treating the first element of the list to be the top, in that case, we should really convert the sequence in the reverse order. Okay? Okay, so now over here, basically you can see that the reason I highlight this in red is because you will see that when we go to version number 2, this is the part we're going to touch to see how we can define them. And then over here, the contract tells us that if you go from 1 until count, so they are position by position the same. But when we go to version number 2, you will see that it's different. Okay? Now, everything else will be just the same. You will see that. First of all, now, whenever we refer to, we write post-condition or precondition, we only use the model. Okay? I'm going to show you some debugging in just a moment. So when we say model.count, think about how this post-condition is going to be checked. Thinking this way. I'm trying to create an empty array, and then I want to ensure that the abstraction model for this stack, doesn't matter if that's implemented using a array or linked list. I want to get a model of that. And the way I construct a model is by using this abstraction function over here. Okay? Once I convert that into the model, I would say the model.count should be equal to 0. Okay, you will see that this post condition over here, highlighted in yellow, is going to remain the same throughout the 3 versions. So we want to make sure the contracts do not change; they stay always the same. Which means for anyone who's going to look at your contract over here, they simply cannot tell what kind of the strategy you're trying to impose. Okay. Now, what about push over here? Again, for push, what we'll say is, as I said before, we'll say model is equal to old model that appended with that element there. Okay. Again, appended is actually some immutable feature, which means it simply returns just another sequence back to you. It's not a command. So you can actually use this query to write your contracts. That's something you want to get used to for this particular topic. And then for pop, well, after removing the last element there, we can also say, model is simply, so front over here. Let me just, again, you can also read the API for, I'll show you very quickly. What does it mean to be the front? Okay, front over here. Front basically is basically the sequence except for the last elements. Okay, let me just illustrate that on the iPad. So if I have a sequence that looks like this, let's say we talk about sequence over here. Okay, let's say I got A, B, and C. That's a sequence of 3 elements. So let me explain some terminology to you. So we call this the first, the remaining part to be the tail. Okay, so terminology. And also, we call this the last. And also everything but the last, the front. Now, because for the sequence over there, we're treating the last to be the top. So now how do we specify the rest of the stack? The front, right? So that will be the rest of the stack. Okay, you can, okay, just some terminology to get used to. That's why if you go back there, you will see simply the model after the pop is simply equal to everything but the last for the old model. Okay, that's something you can just try to run in your head. Guys, any immediate questions before I show you the second version? Okay, you might be wondering, why do we do this? The advantage of doing this, especially the model function that we just introduced, by defining this abstraction function there, we're going to obey both the single choice principle and information hiding principle. Because every time, if I go from version 1 to version 2, after I change the implementation from array into linked list, the only place I have to modify is the abstraction function. And the contracts, I don't need to touch them at all. That's really the benefits. Yes? They can only see the model, yes. Yeah, so that's a good question. What can the client really see? So basically, the client can actually see the model sequence over there, right? They can see that somehow you're trying to model the current ADT, like a stack, as a mathematical sequence. Now, it will be up to you. If you choose not to show any ensure part of the model, in that case, they have no way to tell how you actually convert the sequence from. But for illustration purpose, I show you that anyway. Okay? Yes? Yes, very good. So now an exercise that'll be interesting, you can try that, or maybe I can put it in the exam, would be either way. Okay. Now give it a try. I wouldn't put that one. That would be too easy. Okay. So now let's think in this way. Remember the assumption I made in the iPad notes. I say that let's assume that always for the mathematical sequence, the last element is the top. Now we can make it the opposite. You can say now the first element of the sequence is always the top. In that case, you're going to change the way you define the model fit query. Okay, it's a very simple exercise. You will see how to do it in just a moment. Guys, any more questions conceptually? The concept in some ways is very easy. You just have to understand why we want to introduce this additional query here. Again, it's for better design, information hiding, and also single choice principle. Okay, now let's see how we can migrate to the second version. In which case, we're going to get a linked list. Now, this one is going to be very interesting. Okay. Now, if we migrate to the second version there, first of all, we're going to change the imp from array into linked list. And also, the way we construct this model is going to be a little bit different. Okay, I want to illustrate again to you on the iPad. Again, the concept is very important. Okay, now I want to do something very, okay, let's divide. Again, strategy 1, strategy 2. Okay, and then let's say the red part is going to be the implementation, and also implementation. Okay. Now in this case, actually, let me just go over here. Okay. I think that's exactly what I wanted to draw. So now for version 1, we know that, let's say, again, we got Alan, Mark, and Tom. Okay? Let's say, abstractly speaking, this is the model we want to get into the stack. Okay? Let's say this is a stack we want to implement. Let's say Alan, Mark, and Tom. For strategy number 1, this is what we have. Let me use red to say that's private. In this case, what we will get is the last element is the top. So we have Tom, Mark, and Alan. For strategy number 2, it's going to be a linked list where the first element is the top. In this case, this is the top, so that means we got Tom, Mark, and Alan. So far, so good. Now, how do we create the same abstraction for these 2 different strategies? The way we do this is by creating a mathematical sequence where the first element is always the top. Okay? Sorry, the last element is always the top. Okay? Let me just write it down. Creates an abstraction of the stack ADT as a sequence where the last item is the top. Is top. Okay? Conceptually, this is how the sequence looks like. So we know that we should have Alan, Mark, and Tom. So this is just a sequence. Now, question for you. Here you can see that how do we convert from this imp over here, and let me just call this model as well, okay, just to be consistent with the notion. So this is the model. Okay, that's a model. Now, how do we go from imp into model over here versus how do we go from this imp into the model over here? We want to construct the same model. Yes, question.
I would say if we treat the front in strategy 1 as the first element, and we treat the front in the second strategy as count to the second item.
Yes, you're just talking about how to convert, right? Yeah, we'll see the conversion mechanism in just a moment. Yeah, we'll see that. Okay, so now, guys, I just want you to realize from this illustration here, how exactly, well, you can see that from this implementation into this model sequence, it's very straightforward. You just make it so that the order are completely the same. On the other hand, for this one over here, when you want to convert this order of linked list as implementation, which is completely hidden, you want to go from this into this model sequence here, you're going to do a little bit trick. You're going to do a little bit loop to do it. Okay, that's my point. So you can see that the only difference from the client's point of view is, well, there will be no difference actually, because to them it's the same sequence in both strategies. But the way you convert from this to here or from this to here, they are the same. They are different, sorry. Keep saying the wrong thing. They are different. The way you convert are different. Okay, let's see that very quickly. And then I'll take questions if you have. So now let's go to version 2 over here. Now, okay, you can see that basically, you can see the diagram also on your slides. In here, you can see the green part. The green part means it's always public, never changes. We don't want the counter to change from implementation to implementation. We always say the model as a sequence is equal to the old model that appended with the new elements. Okay? Now, the thing is, in this particular implementation, how do we go from the array into the model sequence? In this case, it's easy. You just go one by one into the sequence. Okay? Now, let me just go over version 2 with you as well, and the version 3 will be very similar. Now, for version 2 here, how do we define the abstraction function? How do we do that? Remember, for the abstraction function there, we are making the following assumption. The last element in the sequence is always the top. It doesn't really change as you change from one implementation to another. However, you can see we got some inconsistency here. In the model level, we say the last element in the sequence should be the top. However, in the implementation level, it's strategy number 2. The first item in the list is actually the top, right? So how can we convert this implementation into the abstract model? Okay? See what the issue is? It's easy. You can simply do a cross loop over here. You can simply just also look for some commands in the sequence. Okay, also leave it to you. There's something you got to explore. So they got something called prepend. You keep prepending, right? Rather than keep appending. Okay? And then that's what you get. Let's see how the contract is going to look like. So now remember what we said before for the previous one. This is to say, we starting from 1 until count, we actually got position by position the same. But now if you see that for the second version, it's going to be a little different, which will reflect. So you can see that here we still get from 1 to count, but now we say result at position I is equal to imp count minus I plus 1, right? 100. The implementation. Yes, it's a fantastic question. Yeah. It's a very, okay, let me just rephrase your question. That's a fantastic question. The question was, how can we be sure that the model is always in sync with the implementation? Remember, the model over here is a query. It's a normal query, which means every time you refer to it, it's going to be called. And whenever it is called, it's going to convert from the latest value for the implementation. Now, let me just strengthen your understanding just a little bit more. Now, let's say if I go to this particular thing over here, let's say over here. When I say model is equal to old model.deeptwin. Now, thinking this way. Remember the IFO compiler or runtime is going to cache the value of any old expression before you try to execute the command, right? In this case, since you say old model.deeptwin, so it's going to cache that old model completely in the deepest level, and then put it aside. And then let's see what's the new model and compare both. Okay. Now let me show you one more thing very quickly. So you can also try to reproduce that when you go back. Okay. When you download the source code, there is a class called test stack. Okay. So now I want you to go to another one feature called test push. I'll show it to you. Exactly answering Andrew's question a little bit more. So let's say we're trying to test the push over here. Let's say we try to push A and then push B. I put a breakpoint over here, okay? I put it there. And let's try to run the debugger and see what happens. Okay? If I say run over here, okay? So now you can see that the system execution is paused over here, right over here. So now we're going to execute a push, okay? Meanwhile, I'm going to remind you what a push is about. You can see the push over here is model is assigned to old model.deeptwin.appended by, which means before we try to execute the body of the push, we are going to cache the value for model first. That's when we're going to call it the first time. Okay? Now let's see that very quickly. Now, at the moment, before we say push B, we already have A in the stack, right? We previously pushed A already. So now, if you try to call the model before the second push, the sequence is going to be just A. Okay, let's verify that. Now, if I say step into, okay, if I can find it. Okay, so now execution, step into. But in your case, somehow my GUI has been crammed, because of resolution. But you can step into. If I say step into, you can see that this one calls the model the first time. So this is when we cache the value. And then let me just go to the end. Let me just go, okay, sorry. Got to do it a not very convenient way. Step by step. Step by step. I can simply, you know what? There's a trick in the debugger. Let's say I want to go to the end. I can simply put it here and then say run again. So now I'm at the end. Okay? So now if you can just go to the result. Remember, this is the model query over here. So that means the result is of type sequence. Okay? You can see that at the end of the loop, what we will get is A. Just before we try to push B. Just before that. Okay? Let's go just a little bit further. I want to show you. Okay, so now let's go a little bit further. Let's say step over, step by step, execution, step by step. Okay, so now let me just do one more. Sorry, it's a bit unpleasant. Step by step. Okay, now we're in the push, right? So now what's going to happen is we're going to execute a push, but the old model has been cached already somewhere. Okay, so now we say execution and then step by step. Now, if we try to step into this particular comparison, what's going to happen is we're going to call the model again. In this case, it's going to actually get a result for the latest one, which would be A and B. Okay? That's good. Okay, and then I'll stop. Okay. Okay, and then similarly over here. Now, one more thing, one more time. So over here, you can see that the contract remain exactly the same. It's just that in the second strategy over here, we just changed the way we construct the model. So the model is always the same. It has the consistent interpretation. As long, if you change from one implementation to another, just make sure you convert the right model accordingly. Yes? Oh, you know, prepend, you know what? Think of pretend like at first. Prepend. Append is like at last. Okay, how about I write it down? Okay, so there will be some sequence feature over here. When you say prepend, it is basically equivalent to at first that you learned before in the singly linked list. And also you got append, and then that's basically equal to at last. Okay, good. Okay, that's good. Okay, that's number 2. Okay, you can go over the third version as well. Okay, now for the third version there, you can see that you only have to change, again, just the abstraction function a little bit, just to be consistent with the current implementation, and then the contracts remain exactly the same. Okay, okay, I'll let you go over the rest. Okay, guys, any questions until now, before I summarize what we have done? And then I'll show you a little bit more details about the math models, which will hopefully be helpful to the lab and also exam later. Okay, let's summarize very quickly. Okay, let's summarize the point. So now we presented basically what we learned before. If you simply just write your post condition using implementation attributes, which are exported to none, in that case, it violates the information hiding and single choice principle. You can refer to the previous slide. So that's why we created an abstract model instead. So for each ADT, like your class, stack, queue, double-ended queue, binary tree, whatever, or your analyzer, for example. And you can say create an abstraction by using a mathematical model. I would say, so you might be wondering, how do you link this into your real-life application? So I would say for the mathematical library, the most complicated type you have is called relation, which you learn briefly or quite thoroughly in 1090, right? Mathematical relation. I'll give you some review slide you can refer to, and I would say for any real application there, you can always try to create an abstraction in terms of relation, because relation is like a graph. A graph is the most general data structure you might have. Okay? I'll show you more details in just a moment. Okay, and then in the case of a stack, we just use a sequence. And then we define an abstraction function which will convert from whatever implementation you have into the math model. So when you go from one implementation to another, you only have to change the way you construct the mathematical model. But the type of the mathematical model doesn't change, always a sequence in this case. Okay? Okay, so now we write the contracts always in terms of abstract math model. This is why for lab number 5, I say that for you to define any pre or post condition, if I see, especially the post condition, if I see that you try to use any of the exported to none implementation attributes, 0. It's a little bit similar to when you were in 2030, when you were trying to do recursion. They say that if you try to use any loops in your code, 0. Right? So now in this case, I want to make sure you only use a math model to write your post condition. Okay? So read the instruction more carefully for lab number 5. Okay? Okay, so when you change the implementation from one version to another, all you got to change is basically how you actually create an abstraction function. Okay? And because there's only one single place you change, namely the abstraction function, so single choice principle is obeyed. Okay? Guys, any questions before I give you a little bit of review for the math? Okay? Are we okay? Yeah, okay. Okay, basically, from now until the end, it's pretty much like a quick review of 1090, the relevant parts. So I'm going to go in a little bit rush way, but if you really got anywhere you don't really get, feel free to stop me. Okay, that's the advantage of attending the class, right? You can always stop me here. And then I will also show you some small detail for the math library. Okay, and then I'll give you some example test. Okay, set is very easy. Set we got, okay, and then you got the order does not matter. You will see that in the math model, there's also a type called set. Oh, actually, I'll let you search for that. If you go by the Apple Studio, if you got math model set, you will see the set type as well. Okay, so now for the set, I want to just talk about, make sure you're comfortable with set comprehension notation, because the way I'm going to define the relation operators, I'm going to use set comprehension very quickly. You put whatever expression over here to the left of the vertical bar, some expression there, and then you put some constraints over here, usually separated by conjunction. And then that's going to say what members will be included in the final set. Okay? Very easy. For example, what would be this set contain? What would it contain? Well, I'm saying that I'm going to grab all the x in this final set, and then x should be between 1 and 10. Also, x is odd number. That should be 1, 3, 5, 7, 9. Okay? Very easy. Okay, I'll let you go through the rest. Set is really easy. Okay. Now, what can you relate between the sets? So you got subset. Okay, make sure you're okay with subset relation, right? And also equal. What does it really mean when two sets are equal? That means they are a subset of each other. Okay, we can also go through the definition. And also proper subset. Proper subset means they cannot be of equal size. It gotta be strictly smaller. Okay. Okay, and also you can do, for those of you who are not really sure what union, difference, and intersections are for the project, here also some review for you to look into in case. Okay. What does it mean to take a union? Well, take every element in the two sets, right? What does it mean to be intersection? The element in both sets. Difference means in one set but not in the other. Okay, I'll leave the detail in definition to you. I want to focus more on relation. Okay, now power sets. Now, what does it really mean to a power set? Question for you. Usually, this is what we write, power set. What's the power set of A and B? What's the power set? If anybody can tell me quickly. Power set. Yes? An empty set, right? It's basically the set of subsets. Okay, set of subsets. So basically, it's going to be, let me just show you very briefly how you can systematically enumerate them. It's going to be a set, and every member there is going to be a set. So the set can be of size 0, 1, and 2. And the 2 will be the maximum. That will be the entire set. Set of size 0, empty set. The largest subset you can get will be the set itself, A and B. And then you can also get in between. What will be the set of size 1? It can be either A or it can be B. Okay? And then, not surprisingly, 1, 2, 3, 4. Why do you have 4 members there? Because 2 to the power of A and B over here tells you you can either choose A to be included or not to be included, B to be included or not to be included, right? So that will be 2 to the power of this cardinality of the set. That's power set. So why is power set relevant? Because we can kind of use power set to define relations in just a moment. Okay, power set, you can go over that. So now, cross products. Cross product is even more relevant. Cross products somehow correspond to tuples that we talked about so far, okay? Let's say, for example, I'll give you one example. Cross products. If I say over here, I have A, B, cross products, and also X, Y. The result is going to be a set of tuples. And what's the size of each tuple? Depending on how many things I'm trying to cross product with. I got one thing and two things. So it's going to be, each thing over there is going to be a pair. Over here, I'm going to choose one thing from the first set and choose another thing from the other set. So it can be AX, it can be AY, it can be BX, it can be BY, right? Something like that. Okay, very easy. And of course, in general, if I just add another thing over here, I can be maybe this and whatever, actually, something like that, right? You can just add another dimension there to the cross products. Okay. Okay, now you can also do some little exercise over here for you to review. Now let's come to relations. What's really relation? So relation is a big class for you to get used to. For the lab number 5, you only have to deal with something called function. Function is a specialized form of relation. I will give you the formal definition in just a moment. But for relation here, it's more general. That's something you should know for the exam. So you do have time to actually get used to it. For relation, basically, it's just a set of ordered pairs. Okay? So every element in the relation is a pair. Okay? How do we define the relation? Let's say here we got two sets, 1, 2, 3, and we have A, B. Okay? First of all, if I say S cross product B, okay, so now let me just put it on my iPad. And then 1, 2, 3 cross product A and B. Okay? So now, what will be the size of these cross products? I heard 6, right? Because you know that cardinality of this set here is 3, and this is 2. So that means we actually got a set over here. For example, 1 and A is one of them until, also I got maybe 3 and B, etc., etc. So I got exactly 6 pairs. Okay? So now, how do we define a relation? A relation is simply just a set of pairs. Okay? So now, based on, let's say this is S, this is the T. Okay? So now, if I say from, so this is, we so-called, this is the largest relation. Okay? For S and T. Because these are all the pairs you can get. So the largest relation will be size 6. So what will be the smallest relation? Smallest one. Well, what will be the smallest relation? A relation is simply a set of pairs. In that case, what will be the smallest one? Empty set, exactly. Okay. So empty, so this largest one, empty set will be the smallest relation. And everywhere in between of different sizes will be different relations you might have. Okay? Again, if you are not really comfortable with this kind of notation, you mean, don't speak to me. That's not really the main thing for this course. I just want to review very quickly. Okay? So empty relation, the smallest one, or S cross product T is the largest one you may have. Okay? Anything in between will be also a relation. Okay, now let's define some terminology. Domain will be all the first elements in the relation, domain. What about range? All the second elements, okay? That's a range. Okay, you can also see the mathematical definition there. Okay, so now, and the way you can express about all the possible relations that you can have for between S and T is, you can simply, we know that S cross product T is the largest relation you can have. So any subset of that should be a valid relation, including itself. So that's why we put the cross power set over here. Okay? Okay? Now, here comes more relevant to the math model. Okay? So all the mathematical operation you can perform on a relation, they are supported in the math library. And that's something you want to get used to. That's because we can use the mathematical relation operations to write contracts. So let's give me one example. Let's say the birthday book or dictionary. You can think of the dictionary as a relation where the keys are the first elements and the values are the second elements. And then you can just use the various operation like a relational image or relational overriding, to specify different features. I'll show you some example. Okay, let me just, so let's just try this very quickly. So domain will be the first element. In this case, that'll be A, B, and C, and etc., right? There's going to be all the first element, in this case, A, B, C, D. Okay? Actually, this should be E and F as well. A, B, C, D, E, F, all the first elements. Okay, I'll change that. And the range will be all the second elements, in which case there'll be 1, 2, 3, 4, 5, 6, right? Okay, very good. What about inverse? Inverse will be I reverse the order of the first and second element. In this case, So now rather than A1, I got 1A. Rather than B2, I got 2B. Okay, also very easy. So these are all the features of the mathematical library, the relation class. That's why you should really get used to this. Okay, let's see something that's slightly more complicated. Something called domain restricted. First of all, if you have a relation like this for R, I say R dot domain restricted. So first of all, what you will is a query, it's not a command. It's not going to change R. It's going to return just another relation, and that new relation there has the domain ds only. Okay, let's see the mathematical definition. It's going to be dr, the domain and the range value here. First of all, dr is a member of the original relation, but d is only in ds. Okay, for example, let's say over here. If I say R over here, dot domain restricted to AB, that means I'm going to return a new relation there, which is pretty much similar to the original R, but I'm only going to keep those values for domains A and B. In this case, you can see only A and B are here, right? For example, C is taken out, D is taken out, it's not included, and also E and F are not included. Are we okay? Make sure you're okay with this, because we got another 3 which are pretty much similar. Okay. Now let's do something very symmetric. So now I can, in this case, I say that I'm going to return a new relation there where all the domains are going to be exactly ds. But now let's do another way that's opposite. Domain subtracted. I'm going to return another relation there where the ds is simply not included as domain. Okay. Now let's say over here, if I say R the domain subtracted, so now what I would get is I'm going to get everything but the domain is not in ds. Okay, over here. So now what would it be? Well, you can see I only got C, D, E, and F left. So A, B are not included anymore. Okay. Guys, are we okay? Okay. So these are something very simple. It's not difficult. I just want to go through them with you very quickly. Okay. So now you also got range restricted and also range subtracted in a completely symmetric way. Okay. I'll leave you to read it. Okay. Yeah. Okay. So I will give you some example tests. So basically, everything we talk about over here, they have been already implemented for you. So they are the library classes from the math model. Yeah.
But what's the data type of RS?
RS, yeah. RS and DS, these are type set, which I'll show you in just a moment. You will see that. Yeah. You also need to use them maybe for your lab. Okay. I'll show you. Okay. Just hang on. So the question was, how do you create a DS and RS? The answer is you're going to use also the mathematical library class called set. Okay? They also got constructor for you to do. Okay? Okay, we got 5 minutes. I think we got time. Hey, okay, this one is a little bit tricky over here, overridden. This is how you can think of overridden. Now, let's imagine that you got dictionary class. Whenever we say add entry, let's say now we don't have the precondition to say if you want to add a new entry there, the key may be there already. In which case, we're going to replace the corresponding value with that associated key. Okay, we're going to override. Okay, so now, let me just give you one example over here. So this is the complete, the mathematical definition for that. You can go over that. And now, let's say this. If I say R dot overridden A3 and C4, so what does that mean? That means I'm going to return just a new relation where the new relation there, whenever we talk about A or C, I'm going to agree on this particular set over here, rather than the original one. So now that means I'm not going to have A1 anymore. I'm not going to have A4 anymore. Rather than that, I'm just going to have A3, okay, just according to the new one. And also for C4 over here, I'm not going to have C3 anymore. I'm not going to have C6 anymore. Okay, okay, you can go over again the reasoning here. So that's a new relation. So I would say overridden is really the critical feature you should really get used to. So again, I included all the complete definition here. Hopefully you can see that. Okay. Okay, functions. Well, for functions, I will leave this part to you. You can also read them, the mathematical definition. Okay. Okay. Okay, you may want to see what injective functions is. That might be useful. Okay. Now, just a few more slides and then we're done. Okay, just a few more minutes. One thing to show, one thing to pay attention to. in every mathematical library class, we actually got basically two counterparts. For example, for domain restricted, you also got a command version for domain restrict. You will see that one is command, the other one is query. You can use either. Okay, I'll show you one example over here. So when I say r.domain restrict, this one here, it does not return any new relation. You simply modify the context object r. Just change that so that it becomes its old version of domain restriction. Okay. On the other hand, I can also call the query version domain restricted. In this case, I'm not modifying the r. I'm just returning a new relation. Okay, so you might be wondering, so which one should I use? This is the rule. Example test you can just go over. I kind of show you how you can use domain subtract and domain subtracted. Okay. Now, so this is the rule for you to follow. So you want to use the commands when you want to define your abstraction function. For example, you can see over here, the append over here is the command version in the mathematical sequence. On the other hand, when you try to write contracts, use the query version. In this case, you will see that you got appended over here, right? Appended and append, they're the counterparts of each other. It's just that the append simply changes the current objects of the sequence. On the other hand, but you cannot use any command in the contracts because they don't return anything. So you're going to use the query version. Okay. All right. For the exam, you need to familiarize yourself for relation and set. And any questions, we might have 1 minute to answer. And then, are we okay? Yes.
Does the final exam have a programming component to it?
Let me stop the recording.